Assalamu alaikum wa rahmatullahi wa barakatuh. This is the last video of Chapter 4 Mechanical Oscillations Part 2. At the end of this video, you are going to be able to explain free damped oscillations and analyze its graphs of energies. First, it's good to remember, in the previous videos we have mentioned that free mechanical oscillations can be damped or undamped. An oscillation is characterized by its period, frequency, and amplitude. The nature of oscillations made by a free undamped oscillator is simple harmonic motion. In free undamped mechanical oscillation, the amplitude and the mechanical energy are constants. The differential equation of a simple harmonic motion is x double prime plus omega 0 x equals to 0, and finally the time equation is x equals to a sine omega 0 t plus phi, or x equals to a cosine omega 0 t plus phi. As we have already seen in the first video, that free oscillations are divided into undamped oscillations and damped oscillations. So far we have studied the undamped mechanical oscillations, where there are no non-conservative forces, mechanical energy is conserved, the system oscillates with constant amplitude, and its period is called the proper period T0. Now, in the damped oscillation, there will be non-conservative forces, and the mechanical energy is not conserved. The system will oscillate with a decreasing amplitude, with period called pseudo-period, where t is greater than t0. We consider a horizontal elastic pendulum which moves through air and experiences a friction force. The solid is shifted from the equilibrium position and released without initial velocity. The first graph shows the variation of the position x as a function of time. It is represented with a purple curve, and the variation of the velocity, which is represented with the orange curve. We can see that the amplitude of x and v decreases as time goes on. And note that when x is 0, v is not maximal. While the second curve shows the variation of energies, the mechanical, the kinetic, and the potential energy as a function of time. Starting from 0, v was 0, then the red curve, which starts from the origin, corresponds to the kinetic energy. x0 was maximum, so the green curve that starts from a maximum corresponds to the elastic potential energy. There is an exchange between these two energies. That is, if the elastic potential energy decreases, the kinetic energy increases. But it is noted that these energies do not reach the same maximum. Then the amplitudes of these energies decrease as a function of time, and so is the mechanical energy, which is the sum of both and represented with a blue curve, decreases as a function of time due to the friction, where the work done by this friction is not zero anymore. What is this friction and its power? The expression of a friction at time t during the oscillation is given by F vector equals to minus h v vector, and it will be given to you in the exercise, where h is the damping coefficient and v vector is the velocity of the center of mass of the object at any instant. The power of this friction force is given by F vector dot v vector. So, replacing f by minus h v vector, we will have the expression minus h v squared. The question is, why are we interested in the power of a friction? Actually, the instantaneous power is the derivative of the mechanical energy. Therefore, the derivative of the mechanical energy is minus h v squared. As we have done before, to study the motion of this pendulum, we first look for the expression of the mechanical energy of the system, solid, spring, earth. At any time, it is the kinetic energy, which is half mv squared, plus the gravitational potential energy, plus the elastic potential energy. Now, taking the reference of the gravitational potential energy passing through the center of mass of this solid, then the gravitational potential energy becomes 0. Finally, the expression is half m v squared plus half k x squared. Following the same steps, method 1 to find the differential equation is the mechanical energy. So at any instant, it is half mv squared plus half kx squared. But now there is a non-conservative force, and the mechanical energy is not constant. The derivative is not 0 anymore. We can write it as minus hv squared. Following the same steps of derivative for x squared and v squared, reducing 2 and half, and adding hv squared in both sides of the equation, we can find finally that the differential equation is given by x double prime plus h over m x prime plus k over mx equals to 0, and this is the second order differential equation without a second member which governs the variation of x in the damped oscillations of an elastic pendulum. The second method is Newton's second law. We start with a system, which is the solid. The external forces acting on the system are the weight, which is vertically downward, the normal reaction, which is vertically upward, the tension, which is to the right, finally the friction, which is also to the right. According to Newton's second law, which is sum of forces equals to ma, projecting along x-axis, which is to the left, we can write it as minus hv I vector minus kx I vector equals to ma I vector. Replacing the acceleration by x double prime and writing this equation algebraically, we can reach the differential equation the same as we have found with the first method. But you should know that for x equals to plus or minus xm, v is 0, but for x equals to 0, v is not maximum anymore. What is the solution of this differential equation? This differential equation is of the form x double prime plus 2 delta x prime plus omega 0 squared x equals to 0. Where here we have a new term 2 delta x prime, where delta is h over 2m, and we are going to study these oscillations according to this factor h over 2m. If h over m is less than the radical k over m, which is omega 0, then the solution is x equals to a exponential minus h over 2m times t sine omega t plus phi, where a, omega, phi are constants. A can be positive or negative. The amplitude here is taken as the absolute value of a exponential minus h over 2m t, which decreases exponentially with time. Will the pseudo-pulsation change in this type of oscillation? Yes. Omega here becomes the radical of omega 0 squared minus h over 2m squared, where the pseudo period, which is 2 pi over omega, is greater than the proper period, since omega now is smaller than omega 0, and t increases with the value of the coefficient h. But we have mentioned before now that we have 3 cases of damped oscillations. How can we see these oscillations according to h? If h over 2m is less than radical k over m, then this oscillation is called slightly damped. But if h over 2m is slightly smaller than radical k over m, which is omega 0, then it is called largely damped. But if h over 2m equals to omega 0, then the system does not oscillate, and this is the case of critical damping. In this case, the system returns to its equilibrium position in the fastest possible time without making oscillation. Beyond this value, the system takes a relatively long time to return to its equilibrium position, so this is the case of overdamping. To compare between the damped and the undamped oscillations, we took into our consideration two examples, the elastic and the compound pendulum. Try to observe the difference in differential equation and in the characteristics of this oscillation. As usual, let's end with this application. The abscissa of a block of mass m equals to 125 grams of horizontal elastic pendulum is given by x equals to 0.101 exponential minus 4h times t sine pi t plus phi, where h is the damping coefficient, phi is the phase at the origin of time, and they are both constants. At t0, x0 equals to 0.1 meters, while v0 is 0. V is the algebraic value of the velocity of the block. Now, the first part, using one of the initial conditions, show that the phase at the origin, phi, is 1.42 radians. As usual, pause the video and think of the answer. At t0 equals to 0, x0 was 0.1 meters. Just replace this value in the expression given in the question and try to solve it by calculator, where exponential 0 is 1. We can find that sine phi is 0.99 and finally phi is 1.42 radians. The second part is using one of the initial conditions of motion, determine the value of the damping coefficient h. So we can use the other one, which is v0 equals to 0. And we know that v is the derivative of x. Using u times v prime equals to u prime v plus v prime u from math, and we know that the expression of x is the multiplication of two functions depending on time, the exponential part with the sine part. Remember that the derivative of exponential u equals to u prime exponential u, and the derivative of sine u equals to u prime cosine u. Then replacing v0 equals to 0 at t equals to 0, by calculation we will get h equals to 0.111 kilograms per second. These are the main ideas that are mentioned in this video. Study them well, and this is the end of the last part. Thank you for watching.